So, when it comes to storing your most important data, two massive names always come up: ZFS and Btrfs. Now, they both promise to keep your files safe, but as we're about to see, their fundamental philosophies on how to do that are worlds apart. We're going to dive in and find out which one really has your back when something as simple as a power flicker threatens to wipe out everything. Let's just start with a question that honestly is a little unsettling. Think about it. Do you trust your hard drives? What if, right now, your most precious files, your family photos, critical work documents, are just silently degrading? This is a real thing. It's called silent data corruption, and it can make your data completely useless without giving you any warning at all. Yeah, this quiet enemy is often called bit rot, and to fight it, modern file systems use something called checksums. Just think of a checksum as a unique digital fingerprint for your data. When you save a file, the system calculates this fingerprint. When you go to read it back, it calculates it again. If those two fingerprints don't match, well, you know the file is corrupt. But here's the thing, just knowing your data is broken isn't really a solution, is it? But you know what? Detecting that kind of corruption is only half the battle. For anyone out there using a traditional parity-based RAID, like the super common RAID 5, bit rot is actually the least of your worries. There is a much, much more dangerous problem lurking under the surface, a built-in vulnerability that can nuke your data in an instant. It's known as the RAID 5 write hole, and it's a critical, fundamental design flaw that can get triggered by a simple power flicker. In that split second, your entire array can be left in a broken state where your data and the parity that's supposed to be protecting it are just permanently out of sync. So how does this even happen? Well, it's because of this really risky four-step process called read, modify, write. See, to change even a tiny piece of data, the system has to read a whole chunk of data in parity, modify the part it needs to in memory, calculate the brand new parity, and then write the new data, and then the new parity back to the disks. Now, if the power cuts out right between writing the data and writing the parity, boom, you've just fallen into the write hole. Your RAID array is now telling a silent, permanent lie. And the worst part is, it has no idea. This exact problem is why ZFS was created. It's not just another file system. It's a total rethinking of how data storage should work, built from the ground up with one thing as its absolute, non-negotiable priority: data integrity. The secret weapon that makes ZFS so powerful is a really simple but absolutely brilliant idea: copy on write. And what this means is that ZFS never overwrites existing data. Ever. When you modify a file, ZFS writes that new version to a completely fresh, empty space on the disk, leaving the original data perfectly intact. And this is how ZFS so elegantly makes the write hole impossible. The new data and its new parity are written together as a single transaction to a brand new spot on the disk, and only after that write is confirmed as 100% complete and safe does the file system update its internal map to point to this new data. So what happens if the power fails mid-write? Nothing. It's no big deal. The map was never updated, so the system just boots up and still points to the old, perfectly consistent data. The corruption was prevented before it even had a chance to happen. So the crucial takeaway here is this. Because of copy on write, the state of your data on the physical disks is absolutely guaranteed to be consistent at all times. The write hole isn't just patched over. It is architecturally impossible. But wait. ZFS has another superpower: self-healing. When ZFS reads a file and sees that the checksum doesn't match, it doesn't just throw up an error message and give up. No, it automatically finds the good correct copy from your other redundant disks, gives that good data to you, and at the same time, it fixes the corrupted block on the faulty drive in the background. You might not even know it ever happened. It just works. Okay, so now let's turn our attention to the other contender: Btrfs, often called Btrfs or Btrfs. It's also a modern copy-on-write file system, but it was really designed with a completely different primary goal in mind: flexibility. And this flexibility is hands down the main reason you might choose Btrfs. ZFS is incredibly powerful, sure, but it's also very rigid. If you want to add more storage, you have to add a whole new group of disks all at once. Btrfs, on the other hand, is amazingly flexible. You can just grab a single drive, any size, add it to your pool whenever you want, and tell it to rebalance the data across all the drives. For home users, that is a huge, huge convenience. But, and this is a huge but, this convenience comes at a terrifying cost. Because for all its cool features, Btrfs is hiding a really dark secret, specifically when it comes to its parity RAID implementations. And hey, you don't have to take my word for it. This is a direct quote from the official Btrfs documentation about its RAID 5 and RAID 6 modes. It has warned users for years not to trust it with production data. This isn't just a bug, it's a known, fundamental problem with the design. Okay, so this is probably what you're thinking right now. Hold on a second. If Btrfs is also a copy-on-write file system, how can it possibly have this problem? Shouldn't it be immune to the write hold just like ZFS? And, well, the answer, unfortunately, is a big fat no. And here is the absolutely critical twist. While Btrfs uses copy-on-write for your actual data, its RAID 5 and 6 implementation does not use it for the parity information. It writes the parity in place, which recreates the exact same read-modify-write cycle and the exact same catastrophic write hole vulnerability that ZFS so brilliantly solved. It's a fatal flaw right in the design of its parity RAID. So, with all of that on the table, how on earth do you choose? Well, it really comes down to a clear-eyed look at what you value most: absolute, bulletproof integrity or ultimate flexibility. All right, this table really brings it all into sharp focus. You can see it right there. Where ZFS is fully copy-on-write, Btrfs is not, at least for parity. Where ZFS self-heals corrupted data automatically on the fly, Btrfs needs a manual command. And the big one, ZFS has production-ready, safe parity RAID that is immune to the write hole, while Btrfs's is unstable and vulnerable. The whole trade-off is right there: ZFS's rigidity versus Btrfs's flexibility. So the choice is actually pretty clear. You should choose ZFS if your absolute #1 priority is data integrity, period. For your critical files, your family archives, anything you simply cannot afford to lose, its architectural safety and its battle-tested parity RAID make it the provably safer choice, as long as you're okay with its more rigid rules for expansion. And you should choose Btrfs if your main priority is flexibility. If you want that amazing ability to easily mix and add drives of different sizes, and you want a more lightweight system, Btrfs is a great option. But, and this is probably the most important part of this whole explainer, you have to commit to only using its stable RAID levels, like RAID 1 or RAID 10, and you have to avoid its broken RAID 5 and 6 at all costs. Ultimately, you see, the choice between these two amazing file systems isn't just a technical one. It's almost philosophical. It forces you to ask a really fundamental question about your own data. Is your digital life built on a foundation of maximum integrity, or is it built on a foundation of maximum convenience?